Good afternoon, everybody. My name is Ben Follett, and I am a structural engineer working for SCIA in North America. I will be the moderator and one of the presenters for today's webinar, plugging ACI318 in today's BIM workflows. Our main presenter for today will be Dr. Gregory Penelis. Dr. Penelis is the CEO of Penelis Consulting Engineers, located in Greece. Recently, he's been working on a bunch of projects in Europe, Moscow, Saudi Arabia, Qatar, and India. He's also recently been awarded the Global Best Project in the Cultural Worship category for the Stavros Niarchos Foundation Cultural Center, which is located in Athens. Also, he recently published his first textbook, Concrete Buildings and Seismic Regions, which is available from CRC Press. The agenda for today's meeting, we're going to talk about a few different things. The first is interoperability between Revit and SCIA Engineer. We'll touch on that lightly because I know that all BIM projects tend to start in a BIM software like Revit. We'll then move into SCIA Engineer and begin talking about the analysis, both static and dynamic approaches in the software. We'll then step into concrete design according to the ACI318 code. We'll look at results both in SCIA Engineer in a report-like interface and also in schedules. We'll then use a separate building to look at some pushover analysis or pushover assessment of a structure. We'll then take some time to look at some real-world case studies, some real-life projects that have utilized this functionality. And then finally, we'll take a few minutes, about 10 minutes for some Q&A. I wanted to make sure that everybody knows that during the presentation, if you want to ask questions in the questions field, we will be answering questions as we go along, and then we'll also ask some of the questions during the process. Okay, so to start, I wanted to start, obviously, where we start all the time is typically in, oh, excuse me, screen jumped here. Back into Revit. There we go. Before we get started, we want to understand that this BIM workflow, including the transfer between Revit and analysis software like SCIA, is really complex. In this webinar, we're going to only scratch the surface of this transfer, so we're going to focus mostly on concrete design, and we won't focus too much on how the transfer works or how the setup of the model in Revit works. If you're interested, we recently actually just hosted a webinar all about transferring data from SCIA Engineer or from Revit to SCIA and different ways to do that. If you're interested in that webinar, you can find it in the webinar section of our website, or you can contact us directly and we'd be happy to set up a special meeting to talk just about interoperability. So what you can see here on the screen is the model that we're going to look at in the webinar. This is obviously a high-rise concrete model. In Revit, we have what we call our CAD's Revit to SCIA link. So it's the link that works based on this analytical model that's used in Revit. This analytical model is the information that's going to be transferred to SCIA. When we're ready to transfer the model, we can utilize in the options field just the export option, and we have a bunch of options for how we want to export things. So in this case, I'm just going to click to export to SCIA Engineer, and I'm just going to save this file somewhere on my desktop in this case. Now when the process begins, we'll start to read the file, or excuse me, the file will start to be read by the link, and then the information will start to be transferred. So the columns, the framing members, the walls, the floors, all the different materials. In this case, I've chosen to keep load cases and boundary conditions like supports and other things. Now all this transferring is done based on mapping tables. Material mapping tables that exist in Revit are mapped to the appropriate mapping tables in SCIA. Additionally, Revit families then are mapped to appropriate profile libraries in SCIA Engineer. And so this mapping, because of that analytical model, is really a one-to-one mapping. And so you really get a great mapping of that information. Now, if there's information in here that doesn't map correctly, or you have really custom families or specialty elements, you can also use the IFC model transfer to transfer elements from out of Revit via IFC into SCIA Engineer. And SCIA Engineer is actually one of the most robust IFC import and export tools. It's actually fully certified for IFC import-export. And so you have a lot of flexibility with how you want to transfer things. Now that the file has actually been written, so it's finished writing file, we can go ahead and close out the import here, close out the service, and we can actually open up SCIA Engineer. Now I'm not going to spend the time to actually import this file, but this is the file once it's imported. Again, it's all based on that analytical model, so we can see the analytical model here in the SCIA. And if we had to make any changes, any cleanup, or do anything else, we could utilize what we call the BIM toolbox. So we have a lot of tools to either convert items or align items and make sure that the finite element model works correctly. It's at this point now that I'd like to actually turn the presentation over to Dr. Penelis, who's going to talk about this particular structure and how ECtools and SCIA Engineer are used to complete the concrete design. So I'll switch the screen to Dr. Penelis.
Thank you very much, Ben. Hello, everyone. Please wait for a second so my screen is shared. So, the question is, why? I start with a very standard question. Why use SCIA Engineer? Meaning, we all have our structural software, and why change when there is, as we know, a long learning curve in such a change in design offices? Well, because it has a lot of features that are better than the competition. So it has real actual BIM connectivity. It has a real 3D modeling environment with all the CAD tools we are used to either in Revit or in AutoCAD, meaning you can do curved surfaces, you can trim lines, you can trim surfaces with lines, lines with surfaces, all that. In peculiar geometry buildings, this is very, very important. It has an integrated building design which includes slabs, it includes piles, it includes foundations, foundation slabs, everything. So when you have a model of the building, you can actually have the complete soil structure interaction and also have the complete design. You don't need to save the results of the analysis of the superstructure and then or of the slabs and then send them to another software that's doing the slab design. Everything is done inherently in what is SCIA Engineer, which is a big envelope that includes several modules of analysis and concrete or steel checking. Some more detailed things are that it has a very accurate automatic meshing and refinement tool, meaning that even when you don't have rectangular grid and rectangular slabs, the automatic meshing works very, very well, both for slabs and for walls. This is very critical, especially for walls or slabs with openings, because poor meshing can lead to extremely wrong results. It also has a very good modeling technique for ribs, so, or let's say T-beams. In most software, T-beams are modeled as a T-section, and then the flange is taken into account twice, one from the T-beam and also from the finite elements of the slab itself. Only with modifiers and with connection cardinal points you can change it. In SCIA Engineer you can actually do all that automatically. You just describe the rib hanging from the slab and you also give the flange effective length, and by that you have a composite element of a 1D rib and the 2D finite element for the flange. All these are combined. The stresses of the flange are integrated together with the axial forces and the moments of the ribs, and you have the design of the actual T-beam. This helps in having the correct stiffness for the building. Have in mind that if you do that wrong and you take into account twice the flange, you may end up with a 20% difference in the eigen period of the building. All the concrete and seismic design checks have been developed by structural engineers. Part of these have been prepared by our office for SCIA. You no more need any spreadsheets for moment axial force interaction, for flexure or for shear or whatever. All the checks and calculations are done automatically and they are explained in the report. You don't need to create manually the combinations, they are created automatically, and obviously you can add on to these manual calculations. All the building checks are done also automatically, and also the model for the pushover analysis is prepared also after you finish the analysis and design of the building. So, ACI318, what are the procedures we have in SCIA Engineer? We have the automatic load combinations. We have flexural design of 1D sections and walls and cores. We have the capacity shear design of members, the joint capacity rules for columns flexure, the confinement of columns and the edge elements of walls, the minimum and maximum reinforcement, and the concrete casting joints checks. Also, what about seismicity? What about seismicity? We have all the provisions of ACI318, and the user inputs a lot of the requirements of the code, like the risk category of the area, the importance factor of the building, the seismic design category, the structural system type, and then the rest are done automatically. We have the calculation of purification factors for dual systems. We have automatic identification of in-plan or vertical structural irregularities. Obviously, all these can be overridden by the user. We have calculation of redundancy factor, P-delta effects checks, torsional amplification factors, story drifts, and so on. And also for the pushover, we have the, as I explained, the automatic preparation of the pushover model. It uses 1D fiber element modeling. It actually has an engine prepared by Seismostruct. Seismostruct is an academic software developed in Europe. It's considered to be state-of-the-art on the same level as Zeus or OpenSeas. It does automatically 8 pushover cases, 4 mass proportional and 4 story shear proportional. And have in mind that because it's not a point hinge approach but a fiber element approach, it tackles all issues with RC cores, which you cannot tackle when you have point hinge approaches. So, as already Ben told you, we are going to be dealing with a building you already saw in Revit. But just to get a glimpse of it from a structural point of view, the building, here you see the, one of the lower stories, which are very, very different. You have the Ellipse tower, and also you have some ground stories, which are residential, parkings, and a swimming pool. Here we see the swimming pool level. Here you see the typical story of the tower, where it exists. It includes a set of cores in the center, shear walls, columns in the perimeter, ribbed slabs, one-way and two-way ribbed slabs, as you see on the left and right, and the top and bottom. And the dimensions. It has 43 stories. It has 445 feet height. It is 178 feet in the X direction and 80 feet in the Y direction. Have in mind that these dimensions are of the tower, not of the bottom stories. It doesn't have any basement. It was designed to be on the Hudson River side in Manhattan. I will now go to SCIA Engineer itself. You see here the model of the building, which has been already imported from Revit with all the stories. Some of the features of the model are that the ribbed slabs have been modeled as cell elements or slab elements with stiffness modifiers in order to account for the ribs. Different stiffness modifiers for the two-way ribbed slab, different stiffness modifiers for the one-way ribbed slab. These property modifiers are obviously available in SCIA from the menus. Then we have also the solid parts of the slabs, which are given as subregions. We have the columns, which are described as columns, and the walls, which are described as wall elements, as you see here on the left. Let me just check the wall. So this is a wall with 14 inches thickness. Additionally, the building is fixed at the bottom. We don't have here modeled the foundation, as this is a very heavy model. It has already been solved. Take into account that such a model takes around 5 to 8 minutes to get solved, so it's not very efficient for representation. That's why we have already solved the model. Let me go to the results so you get a glimpse of a deformed shape. Let's say I'm going to choose the deformed shape due to the second eigenmode. So you can see here the second eigenmode. I'll also show you the first eigenmode. You see the first eigenmode, it's full 3D. Then I'll just go and select only one level. I'm going to select the pool level, so just the pool level. And for that I'm going to show the internal forces of the slab due to the ULS combination. Let me turn it a little bit, sorry. So here you see the MX moment. You can also have a look at the other direction, the moment in the slab. In the same way, you can see the rebar contours. You can do the design of the slabs. Obviously, you could model the rib slab as a flange with ribs, but this would be not cost effective for a 45-story building. You can do that for only one story and then extrapolate the results for the remaining stories as far as the slab is concerned. Then I'm going to go to the seismic concrete design of the whole building. Let me show the whole building again. So we see again the whole of the building, the full model. And after we have finished the analysis, we proceed to the concrete design. We go to 1D member and shear wall design. And as we go there, we have a list of selections on the right which we need to decide about. So I'll go through them one by one. So first of all, we have a choice of either designing the whole of the building or selected members. Here we have all the building. The calculation level is either 1D member design only, shear wall design only, or 1D member and shear wall design. We choose the complete design of all members. The shear wall design is very useful when we have a composite building with steel decks. We will not do the pushover analysis of such a model because it will take like half an hour. There are no SCIA Engineer combinations. The combinations are already the automatic ones. We have the option to ignore the BIM axial forces. This is an option that is actually a conservative approach because the beams sometimes, because we don't have a diaphragm constraint in these models, they have axial forces which are beneficial for their design. So we have an option to ignore them. Should for any reason the designer wants to use them, he unchecks this checkbox. The minimum beam reinforcement, flexural reinforcement, is the 4/3 of the calculated reinforcement or not. The other choice is to go with a different approach of ACI. We have it checked here in, although this is used only for, is suggested to be used only for large cross-section beams, like in bridge girders. But because all other software use that, we tend to use it for comparison reasons. the user-defined value of the shear reinforcement yield strength is 60 KSI. The concrete cover is 1 inch. The steel default strength is S60. US customary units the output. And now the seismicity parameters. The seismicity parameters, first of all, we check whether we have seismic design or not. We have seismic loads from spectral analysis. We don't have additional eccentricity loads. The design spectral response amplification, the vertical amplification SDS is 0.2. The risk category is 2. The importance factor is 1. The seismic design category of the building is given as D. The structural system type is A. We can choose through scrolling down. The ductility class, ordinary. We have an overstrength factor of 2.5. We can override the structural irregularity. We have a horizontal structural irregularity of type 2. We also override the vertical irregularity and we define it ourselves. It's type 3. We don't have a weak story. We have an R factor of 4, a deflection amplification factor of 4. The foundation level is defined at 0 of our model. Why 0? Because the foundation is there. If we had basements that are laterally restrained, like when we have a foundation box or a basement box, then this should be the level of the top of the foundation box. Why? Because it affects the capacity design checks, especially for shear walls. So if you, by mistake, give the 0 of your model and you have a basement box, you actually have a more severe check than you would have because, as you know, the seismic forces get, the seismic shear gets inverted when you have a foundation box at the starting of the foundation box. We also have typical rebars from which to choose for the design, and then we go and select Run Design. After we run design, the design process starts. It takes a few minutes, obviously. During this process, first of all the data of the analysis is read, and followingly, there will be a pop-up window where you will be able to check the materials used, the sections you have created. For example, you can see a wall section that's automatically created from the cell elements. Then you continue with the design. You have to assign load cases to specific types, which is, if you name them correctly, it's done automatically. So you have the dead, the live, the wind loads, and we also have an equivalent static load case called EXstat and DYstat. We don't have eccentricity load cases. Why? Because the eccentricity, the included eccentricity has not been checked. And now we see the design of all the beam elements, the column elements, which are hundreds, and the wall elements, which are even more, hundreds. So all these elements are designed for flexure and shear for all the design combinations, and each bar of the bar chart represents one structural element. So after this procedure is completed, you may see several colors in the bar chart. So some of the colors are that you have blue means that everything is okay. White means that you have an exceedance of the maximum foreseen reinforcement. Magenta means that you have a problem with shear. And red means that you have inadequate section or inadequate reinforcement. And green means that you have an extreme axial force. So we had some elements that had exceedance of the axial force, which means that if you go and click there, you see which element you need actually to enlarge in dimensions or change the reinforcement in walls and things like that. As this finishes, you will see that the report comes up, and by clicking on any of these elements on the bar chart, the report directly goes to this element and you see exactly its dimensions, the axial forces from the design. Here we see the general design results. I will not stay much here because these are later on sent to SCIA Engineer. You can obviously save this report also as an RTF if you need to use it, because it's very detailed, but it's exactly the same is included into the SCIA Engineering report with a tabular form. So you see, for example, a wall, you see the required reinforcement, the actions that this came through. You can double click on it and you see the section designer, and you can see in the section designer the moment axial interaction. You can see the stress block, and also the strains in the section. And have in mind that you can see, as I said, this is story 16, pier 22. You see the axial forces, the flexural, the bending moments, and the combination that these result from, either seismic or non-seismic. You also see the confined length in the webs, meaning the edge elements, and then you also see the shear design. After seeing these elements and investigating any issues that one might have, for example, here we see a different core, a very peculiar core shape. These are automatically identified by the analysis model, and they are designed according to the most extreme load case, meaning all load cases are designed, and the one that has the highest reinforcement demand is considered to be the critical. As you see, you have a safety factor for the given reinforcement or a utilization factor, which is well below 1 for this case. We see the reinforcement that we have, which is 0.5%. If this reinforcement was not enough, we would actually increase the reinforcement. Followingly, when we close this report, the report automatically goes to SCIA Engineer. As it's regenerating the report in SCIA Engineer, let me elaborate a little bit also on the actual design process. The design process deals with, as I told you, with beams, columns, and walls. What is very useful in SCIA Engineer is that we have an automatic identification of the walls and cores, and their sections are created automatically, meaning you don't need to go and define each wall element by itself and define openings and spandrels and piers and all these things. These are done automatically, so there is no risk of misidentifying wall elements and having small piers that have not been checked in the design. Also, this is very useful because it helps the automatic creation of the pushover model, as we will see in a while. Finally, obviously this report of the design can be very easily combined with the analysis results. Here we see now let me enlarge it a little bit. So we see here the design results. As you see, here are the general design issues, meaning the frame and wall response amplification factors, the story design drifts, and the drift ratio limits, the elastic stability coefficients for every story, the design combinations that have been used, seismic and non-seismic, and then we have a set of tabular presentation, which is a condensed presentation of the results. This is more useful for a draftsman, not for the structural engineer, the first part of the results, meaning we have the concrete beam, flexural design, all the top reinforcement for all the beams. Then we continue to the bottom reinforcement for all the beams. Here you see the concrete beam flexural design bottom reinforcement. So we have the beam identity, the combination, the dimensions, and the minimum, maximum, and calculated and provided reinforcement. So this is very useful for a draftsman. Also, it's useful maybe for a controller, but not very useful for the structural engineer to get an overview of the building, as I'll explain later. We also have the concrete beam shear design for seismic and non-seismic and seismic cases. And after we finish, then we have the same for, and then we have the analytical presentation of the results. The analytical presentation of the results shows a section at the left and the right and the middle of an element. We have the story, the beam number, its dimensions, and then we have left bottom, left top, center bottom, center top, right bottom, right top, the required reinforcement, the suggested reinforcement, and for each location, the combination that is resulted from. The same for shear. So this is the view, the detailed results pages are the pages that give an overview to the structural engineer of elements that he wants to check. After we finish with beams, I will go on. Let me scroll down a little bit. Then we have the columns. Again, the tabular presentation of the results. And after the tabular presentation of the results, we have the detailed presentation of the results with dimensions, with the rebar locations. Following that, we go to walls. We have the same thing, wall elements, and for each wall we have the top, bottom, the required rebars, where they are placed, also stirrups at the edge elements. Let me also find some more peculiar geometry to demonstrate. This is a C-shaped wall, the same thing. The edge elements, the shear friction test checks, and more or less this is the report. Apart from, added to that, we also have in the folder that we are doing in the folder that we are working on, we have our ESA model. Also an Excel file is created which has the rebar reinforcement for the beams and columns in an Excel tab, beams and columns, where we have all these information in a tabular Excel form that we can use either to include it as such in our drawing or do whatever you want with it for quantity surveying and things like that for beams and columns. They can be filtered, they can be edited. So this is more or less a design procedure that I can present within a webinar. I will now shift to a significantly lighter model in order, which is a 3-story building with a basement, in order to show how fast and easy we can do the pushover assessment. Meaning we have the building analyzed elastically, we go through design. This is now real time. We have already selected to do the pushover analysis after the design. The pushover analysis is done by ACI318, 2013. So now it will go through the design procedure and then automatically continue to the pushover, which you will see being executed in real time, just to get a glimpse how easy it is to do also the pushover analysis of the building you have already designed. So again, we go through the same design with the bar chart. This is a very simple building with walls, a dual system with walls and the moment resisting frames, fully reinforced concrete, no rib slabs, nothing. It's just our benchmark example, to be honest. We also use it in our verification report. After we finish the design, we select to do only one pushover case, not all of them, obviously. And as we see now, the Seismostruct engine is being opened. Obviously, not obviously, one can go through the temporary files of SCIA and check exactly how the Seismostruct model is prepared, meaning how the SCIA Engineer model is transformed into a pushover analysis model for Seismostruct. We have a DXF output for that, and also we have the actual Seismostruct model, so if anyone wants to actually intervene within it in Seismostruct, he can do that. Obviously, he needs to have Seismostruct. But not to do the pushover analysis because the engine is inherent in SCIA Engineer. So we see here the pushover analysis, the steps and iterations per steps. It's a very, very robust engine, so rarely we have stability issues with the results. And as you see, very fast we will have the pushover in the XX direction for this building. We have given a maximum number of iterations 40. We have given a target displacement 3 inches. Obviously this you can change. The more you change that, the total displacement changes, and also the step size changes because it's divided by 20 to start with. And here you see the pushover curve, which is also included in the design report. In the following weeks, we will also have the assessment, the global assessment according to the ASCIA, to the ACI318 provisions for immediate occupancy, collapse prevention, etc. And also we will have assessment on the local level per element. I will not go into any more detail with regards to the actual software. What I will do is tell you a little bit more about which projects have been done using this software. So we have the Blue Center building in Belgrade in Serbia, which houses Microsoft and Procter & Gamble. We see here one part of the building modeled in SCIA Engineer. All of the building was modeled in SCIA Engineer. The Piraeus bank headquarters in Bucharest, Romania was also modeled in SCIA Engineer. These are actually done using the Eurocode part of SCIA Engineer. This is the Ellipse building in New York using the IBC provisions that we presented today. This is the Buena Vista complex in Mexico, which is also done using the IBC provisions as we investigated today. This is a prototype serviced apartment building in Saudi Arabia, in Riyadh. This building was modeled fully in Revit and SCIA Engineer, and it's one of the first Saudi full BIM residential projects. This is the Stardome in Bahrain, a very peculiar type of building where you see also the piles model in SCIA Engineer and the whole soil structure interaction. This is a concrete building with steel elements, with aluminum elements, all of it modeled in SCIA Engineer and designed according to IBC, meaning the US codes. This is the Al Merquab Commercial Center in Doha. This is actually a quarter-mile building, half a kilometer in length, with a continuous foundation slab. Hence it has to be modeled in one model, but it has obviously expansion joints and seismic joints, but not in the foundation and in the basement walls. So because it's under also water pressure. So this building was modeled in SCIA Engineer and checked using the IBC 2012 code. Finally, we have the New Athens National Library, which is a Renzo Piano designed building in the Stavros Niarchos Foundation Cultural Center. and the new Athens Opera House, which is also a Renzo Piano design building. It's the same complex, which are also designed and checked using SCIA Engineer. And actually these two, this complex, the Stavros Niarchos Foundation, has won the ENR 2016 Global Best Project Award. So we would be very happy to have you come by on October 11th if you happen to be in New York for the ENR award ceremony. By completing this, I would like to turn the microphone over to Ben so that he can continue with the Q&A.
Thanks, Gregory, and thank you very much for your presentation. I want to take some time to look at some questions that we had. There were a number of questions about regarding the Revit link. Obviously, we didn't spend a whole lot of time on it. A lot of people wanted to know more about members that were supported, or how it works, or just kind of general questions about families and other things. Obviously, there's a myriad. We could provide you with a myriad of information of how the link works. I think probably the best thing for that is either to, like I said before, to visit our website to see the webinar that we just hosted last month about specifically about connecting Revit and SCIA and using the link and IFC and other like workflows like Grasshopper and Dynamo. We'll follow up with everybody after the webinar, and we can set up a specific time to have a conversation about that. We also had a few questions about does SCIA Engineer support other materials besides concrete? Obviously, Gregory mentioned a couple of the buildings that had other materials like aluminum and steel and wood. And yes, a lot of those materials are supported both for the IBC and for the Eurocode. So it is a full blown FEA software that supports multiple materials. Gregory, we have a question here for you. I guess somebody asked that some of their projects that they've recently taken on require seismic dampers. How would or can you handle buildings which required seismic dampening in SCIA Engineer?
Well, we have actually modeled such a thing in the Athens Opera House. We have a ferrocement canopy on top of it, which is 330 feet by 330 feet, and it's fully supported by springs and dampers. So you can do that, but you cannot have the non-linear behavior of it, meaning you can have an equivalent linear damper. If you want to have a viscous non-linear damper and do a time history non-linear analysis, it's not possible within SCIA Engineer, because SCIA Engineer only deals with elastic analysis and non-linear static analysis at the moment. So you can do the equivalent linear damper very easily, but you cannot do non-linear time history analysis with viscous plastic or viscous elastic dampers.
Okay, thanks. I had a question come in about how would you, in SCIA, or in your experience, how would you deal with or use SCIA to design a structure that had a weak story or a soft story? Is there specific checks that the software can do, or are there specific things that you've done using the software for those types of stories or parts of buildings?
It's exactly as you say. The design part of the software actually lets you define if there is a weak story and to amplify the shear forces during the design according to this soft story effect. Also, even one could actually model the actual building, meaning if it has a soft story due to CMU infills, he could actually model the CMU infills with cell elements that are not participating in the design, but actually create the stiffness effect for the whole building. So yes, you can take it indirectly in the design by using the special ASCIA, the ACI318 procedure, or you can not do that, but actually model this soft story by modeling your non-structural elements that create that effect.
Very good, thank you. How would you deal with, I know you mentioned something I think earlier, but how would you deal with, in your analysis model, how would you deal with for cracking in specific elements using SCIA Engineer?
What do you mean by cracking?
So like if yeah, sure. So in the ACI, I think I could probably handle the question. So in the ACI, there's some provisions for the cracked moment of inertia for beams and columns and stuff like that.
Yes, of course, and not only that, you shouldn't design a building with uncracked properties. Usually, all this is at 50%, and you can give it through section modifiers at 1D elements and also 2D elements. So SCIA Engineer obviously has these property modifiers for either 1D element sections or 2D cell elements or all slab elements. And you can define exactly how much cracking you want to consider, although the code-defined value is close to 50%.
Okay, thank you. We had a couple questions. I can take this one. We had a couple questions come in about precast and pre-stress design. It's certainly it is available, and it is an option to design, or to analyze and model pre-stressing and PT slabs, both in the Eurocode and the IBC code. The design for pre-stressed and post-tension stuff is available in the Eurocode, is not yet available in the IBC code, but it is on our roadmap. It is on our development kind of queue over the next couple developments. Something that we'd like to, if you're interested, it's something that we're kind of looking for feedback on, in the sense that we'd like to understand better what exactly people want in integrating a PT design and analysis module into a 3D software, which is quite different from historically the way that some American softwares, especially like SAFE and ADAP and RAM Concept work, where they're working on single floors. We had obviously just another kind of general question: is it possible to get a tryout? Yeah, tryout is available at any time. You can visit our website, www.scia.net, and right at the top of the website there would be a button to just register for a free trial. You just have to obviously fill in your name and your email address, and you'll be sent some information about the trial and applying for the trial, and you'll be sent a free 30-day trial. It's a full trial. There's no limitations to the trial, and so you can try it out for free for 30 days. We can also provide people with some of the slides for this presentation if you're interested. So if you want to follow up with us, we can provide you the slides and send that information to you so that you can share it with the rest of your colleagues. There was a question about so there was a question about design and production level modeling. I'm not 100% sure what the question, what they mean by the question, but all the modeling in SCIA Engineer is the modeling in SCIA Engineer. So by default, there's nothing that Gregory did today in his modeling that is beyond standard, let's say. So all the modeling is available in the base version of SCIA Engineer. All the options for modeling slabs and beams and walls and shells and stuff like that are the base functionality in SCIA.
If I might add to that, Ben, I think also maybe they're asking if, especially in steel structure or precast concrete, if it's actually also a production level software. It is, because it actually is fully BIM capable, so you can send it back to Revit and produce whatever you want from it, geometry-wise, if that was the question.
Yeah, thanks for the input. Right now, the reinforcement does not go back to Revit. So if you get real reinforcement, the actual physical modeled reinforcement in SCIA that can be added doesn't go back into Revit. Though obviously those reinforcement schedules can as Excel files and then can be inputted into Revit, but the reinforcement itself does not. I think we have a few kind of other questions rolling in, but I think at this time, and if you have any other just general related questions about the price of the software or about some general stuff with the software. Certainly, we'll follow up with everyone after the meeting. You'll get an email from us. Thank you for your attendance, and we can follow up more specifically and talk specifics about either additional functionality or pricing or how the software is licensed or how we can use the software on a network or on a standalone edition. We can kind of answer all those questions on a case-by-case basis for different people. But I think at this time, if there aren't any other questions, which it doesn't really look like, we can close out the webinar. So first and foremost, Gregory, we appreciate your time. We appreciate your knowledge and your willingness to present to the group here. And so if you have any comments, if you don't have any comments, we'll go ahead and end the webinar.
I would also like to thank everyone for attending and hope to see you in October in New York.
Very good.
Thank you very much.
Thank you, everyone. Thank you for attendance. And the webinar will be uploaded on our website and on YouTube right after the website. So if you need a recording, it will be there. And so thanks for your attendance and have a great rest of your day.